Hi guys, and welcome back to my channel. I know it has been so long, it has been such a busy time for me, but I am ready to dive right back in. So, first of all, I will say that the first part I might go a little bit more quickly through because I did accidentally, again, do that thing where I record the entire thing with no mic and then realize it after. But it's okay because we're just going to dive right back in. So this, for me, is Unit 6, Day 1, Applications of Integrals. I know that for different curriculums it could be different things, but this is basically the idea. It's the day before you move into the washer and disk method and all the other methods. This is sort of the day before that, the prereq, I guess, for it. So it's about finding the integral between two curves. So yeah, we are just going to jump right in and talk about that. So for this first example, let us take this graph where the top half of the graph describes, it's actually two separate graphs. This one is f of x is x squared, and this one is g of x is negative x squared. You will know that in this question this is symmetrical, but it does not require to be symmetrical. It could be literally anything else. If we were to take this, do you guys remember, maybe you will from going back to the beginning of integrals, a Riemann sum? It's not exactly the same idea, but it does have the same vibe. So if you add up all of these little areas, you agree that we'll get the total area, right? So each of these is going to be this height, and they're going to be times as, the limit as n being the number of sections here. The limit as n approaches infinity is going to be when there's, all these tiny little sections, right? So when it's, split up way smaller than I can draw. And then the x value between them, the delta x, will be dx. So, and then the height is going to be what we're going to call here y1 minus y2, which is the height of the top function minus the height of the bottom function. For the sake of all of these problems, you're going to want to you select which one's your y1 and your y2. That's not usually a given. So you want to select the higher up function. And by higher up, I literally mean more positive function as your y1. This is because when you subtract, you want it, the subtraction to go smoothly and not be subtracting the wrong way, because you will get a negative value, which we'll talk about later. So this idea can be summarized into a sort of equation, which is that dA, which is sort of the rate of change of the area. I guess you can think about it as it's kind of this whole thing, except it's not really. It's actually one little sector. Is y1 minus y2, which is this height, times dx, which is this, right? This is kind of the idea of a Riemann sum, sort of, but a little differently. So this idea, now let's see, if we were trying to talk about this total area from here until this line at x equals 4, we could do that as a integral, because if you remember, an integral represents the sum of all of these areas combined. An integral is going to represent this entire area. It is sort of the limit of Riemann sum, as we discussed before, and it is going to be the area under the curve. So we're going to you have to pay attention to your limits of integration, and you have to pay attention to what you're integrating in terms of. So here it's in terms of x, right? Because you are integrating like this with your dx's. So you have to choose the two x values. So here we're going to go between 0 and 4, and we want y1 minus y2 dx, yeah? Now we will substitute, and again, you have to substitute these equations in terms of x. So you want it to be x squared, it's going to be plus x squared, because it's f of x is y1, so it's going to be x squared minus negative x squared, which is the same thing as plus x squared, which is where you get this. We can simplify that to 2x squared. This is really a good enough place to stop for most questions. They do not ask you to evaluate the whole thing. They just kind of want to know that you can write out the integral, so that is really the key part of this. So 2x squared is what you are looking for in this situation. Let us move on to another example. Here we have this example. Also, this is just kind of summarizing the general rule that you should make curve with larger y values your y1. So as you can see here, this is another example. This example requires you to do kind of the same thing. You select this as your y1. It has larger y values at the point of intersection. You find the x coordinates because you need to find your limits of integration, which are basically the edges of the area that you're trying to go between on the x axis. So you do that by finding intersection by setting the equations equal and finding the x values of the points of intersection, which are here and here. Then you would substitute it in and follow the same procedure. But there's not only one way to integrate. You can also integrate in terms of y. So let's talk about that. Here, we have another example, which is y equals x and y equals root x. Y equals x, y equals root x. And you can solve for, so you can do it like this, right? And the way we've done it the other two times in terms of x, which is not that hard. You get, this is me just setting these equations equal in order to get this intersection point. This is very clearly 0, 0, but this intersection point is needed to be found. And when you solve for this, you will obviously get this one again. So you solve for them again just by setting them two things equal, this and this here. You solve for it, you're going to get these 2 points, 0, 0, 1, 1. So, and to get the y value, you can plug into either curve. So now you can write this as an integral. You can write from 0 to 1 of root x minus x dx. You pick root x as your y1, as your first value, as this one, because it is higher up, do you see? So you're going to simplify this, you end up with 1/6. But there's another way to do this. You could also do this by doing these sideways curves, where each of these is the x distance, and there's infinitely many of these. So the thing that's here is actually the dy. So this is integrating in terms of y. This is a little bit different, though. Please do be careful. So this is sort of like a zoomed in version of what I mean by that. So here, you're going to integrate now from y1 to y2, which means from the y value at this point to the y value at this point, which I found out is also from 0 to 1, but it does not obviously have to be in some cases. So now you have to be really careful. It's actually of, here it's of x2 minus x1. The reason it's x2 minus x1 is because, or x1 minus x2, sorry, is because you want to find this distance here. You want to know, like, what this distance is times the little dy. And in this case, just like before when we were integrating in terms of x, we pick our y1 to be the higher value. Similarly, we're going to pick the more positive one here, which is actually the rightmost. So in this case, this is a little bit confusing. When you're integrating with respect to x, like here, you're going to pick this one, which is root x. But when you're integrating with respect to y, this is the rightmost function. So you're going to pick this line, y equals x. So that's because, again, you're doing, if you do y1 minus y2, you're kind of moving this way. So these values will be positive if you go this way. Yes, so that's a really important distinction. You're going to need to find your limits of integration, but in terms of y. So generally, a lot of these problems will ask you to do it both ways. So I suggest just finding the intersection points like so that you have both the x and the y values to work from. And then you're going to need your x2 minus x1. Now, this is really important. Your x2 minus x1 is, say you pick this to be your x1 and this to be your x2, which you should do. Now, you have to write it in terms of y, because this is a dy problem. Do you know what I mean? So you say x1, because that's like this value minus this value, but it's a dy problem, which means you have to write it in terms of y. You have to write x equals in order to get an x2, and your x, sorry, this is wrong. This is supposed to be x1 minus x2. In order to get these x1 and x2s, like that is x1 equals and x2 equals, right? So you need to write it like that. When you're given the equation, we need to say something. Like if y equals x, in that case, that's really easy. But if y equals root x, you need to write that. You need to square both sides and say that y squared equals x. So x equals y squared. So that now when you substitute in, you'll substitute in as y squared, as you can see here. It will be y minus y squared. And here's another idea, is that you really have to choose wisely which one you want. It's not always possible to do both. There are sort of 3 scenarios. Scenario 2, we will explain more in a minute, so don't worry if it feels confusing. Scenario 1 is that it's equally easy, such as this. It is exactly the same process doing it both ways. Scenario 2 is that you can still do it both ways, but it's easier one, and the reason that it's easier is because you don't have to split up the integral, which we'll talk about in a moment. Scenario 3 is that you can literally only do it one way. That scenario is more rare. I will show you an example. This is an example. Here you can do it like this, you see, which is the dx way. By integrating in terms of y, the dy way, like this, does not work. Because when you do it, you would pick this as your y1, and this is your y2. But look, it's literally the same curve. So if you do y1 minus y2, then you're going to end up with, what's this equation? Let's say this is an x squared. But let's just say we're like x plus 3 squared plus 2 or whatever. You're going to end up with that minus itself. So that's just 0. So that's not going to work for you. You can't do it in between the same curve. It has to be between the different curves. So that's why in some cases it really only works to do it one way. In many cases, it is equally easy. And in some cases, it is easier one way. And that is the example that we're about to talk about. So let me take you to a good version of that. A lot of these are not great examples of that. I suppose this is a good example. So take this graph here. I understand this is really, really small and kind of zoomed in, but please bear with me here. So say that you are integrating vertically, which is in terms of x, right? This works consistently, right? You would have a bunch of these infinitesimal lines, and you're always going from a point on this to a point on this, from y1 to y2, from y1 to y2, from y1 to y2, right? You're integrating between these two curves. Please note that this is also bound by the y-axis, and that's fine and very normal, but you are integrating between these 2 points. If you were to do it in the x direction, if you were to do it, well, in the x direction, which is really in terms of y, you would integrate from this point to this point, from this point to this point, on, and note here that in this green section, you're integrating from the curve to the y-axis. But you're always going to integrate starting here. So you're going to go from this point to this point, from this point to this point, from this point to this point. And at some point, instead of hitting the y-axis, you're going to hit the line. So now you're switching the target of your line, right? So originally you're integrating from the curve to the y-axis. Now you're integrating from the curve to this line, which means that you're actually integrating from this thing to this something, and then from this thing to something else, which means there needs to be like 2 sets added together, because you can only ever work with a 2 pair at once, with like a pair at once. You can work with this guy, and then separately, which it goes until this point, and then separately you can work with this guy to this guy. So that requires splitting out integrals, which is what makes it sort of harder, because in this case, it would probably be a better idea to do it integrating in terms of x like this, because then you don't have to split it out. But if you did want to do it that way, or they made you do it that way, or whatever, for whatever reason, you would do it based on, I don't know why that is not going away, but you would do it based on the intersection. So like here you can see you need to find basically this value. So you need to find what this is. And as you can see, that the time at point at which it switches is the y-intercept of this line. So the y-intercept of this line is given by 1, because I think that's given. So that means you split up your integral from 0 to 1, in which point it is interacting with the y-axis. And then again from 1 to 2, at which point is it interacting with the line. So in this case, that would really depend. Your curve is always going to be your y1 because it's always on the right, but your y2 here is changing. Here your y2 is 0 because this line is x equals 0. The y-axis is x equals 0. So you would have, in this case, your y1 minus 0. It's squared, but we'll get there in a minute. In this case, you'd have your y1 minus 0. And in this case, you're moving from your y1 to this. So, yeah. Okay, so that is pretty much it. I do just really quickly want to mention that, like, what I wrote here, which is, and I kind of like briefed on this earlier, but the integral is positive when you do top minus bottom, right? That's kind of why we do top minus bottom. So if you end up with something like, wait, this is going to be an example, so let me just sketch it out really fast. If you end up with something like this would say a line here, right? And say you're discussing this area here, and you know that this area is 11, okay? So this is the polynomial, let's call it P, and this is the line, let's call it L. So if you're doing P of x minus L of x, the integral of that from 0 to 3, let's just say that, right? This value is going to be 11. But if you're doing L of x minus P of x, which is where, so that again, when you do P of x minus L of x, you're saying that your y1 equals do to make it positive, right? But here, if you do, instead of P of x minus L of x, you have L of x minus P of x, then what you're really doing is you're now assigning your y1 to be this smaller value. Do you see what I'm saying? You're assigning your y1 to be this value that's actually smaller at the intersection points, which means that you're going to get a value that is negative. You're going to get the opposite of the positive one. You know what I mean? So, yeah. So if you do this, you should just get negative 11. And you do. Okay, everyone. So that is it. I hope you have a wonderful day. And thank you guys so much for watching. And do not forget to like and subscribe and come back for another video. Bye, crew!